Okay, so here's our isotopes, and we said a minute ago that this is going to be a change in something, but it wasn't electrons. This is going to be a change in the number of neutrons. So the things that are in the middle that are helping to stabilize the atom. So this is where we start seeing atoms to become unstable. So you can imagine some stuff we're going to talk about. So our example that we're going to talk about is actually going to be carbon, because it's a really good one to use, because we actually have some isotopes of carbon that occur naturally, and they're all really neat. So how do we get to all of this? How do we get to these change in neutrons? Well, let me get my, there we go. And normally carbon has 6 protons and 6 electrons, so we're going to draw it both here. Because remember, the number of protons is going to change. In this case, neither is the number of electrons. So what I'm going to do is simply, let's go ahead and add the dot diagrams for the electrons. There's 6, so there's one up here. Let's fill that sucker in. There's another down here. That's 1, 2. Here's 3, 4, 5, 6. So you'll notice something about carbon is that it can hold 8 in its outer shell, but it's got 4. Well, what's going to be easier, gaining 4 or losing 4? Well, the answer is neither, because it's just as far from, it needs 4 more to gain it, and it needs to lose 4 to lose it. So it's kind of halfway in between. It's not the most reactive element that's out there, but it does form some nice bonds. It's just not forming, like, it's not being aggressive about it like an anion or a cation would be. But each one of these electrons can bond with another, and lots of times we see hydrogen and carbons form together, and that's the beginning of organic chemistry, carbons, hydrogens, and oxygens, and they can form up to 4 bonds. 1, 2, 3, 4 bonds. So another electron, another electron, another electron, another electron. That makes it feel like it has a full outer shell. But what we're changing here isn't going to be the number of electrons, it's going to be the number of neutrons. So normally, this is something we call carbon 12. And where do we get that number from? Well, it's the number of protons plus, excuse me again, plus the number of neutrons. Right? So you can imagine that carbon 12, if 12 is the number of protons and the number of neutrons, we know it's got 6 protons, so how many neutrons must it have? Well, it also has 6, right? Those 6 neutrons help stabilize those 6 protons as all these electrons are zipping around, pulling on it, and it keeps the atom good and stable. But here's the kicker. I'm going to redraw this. I'm just going to copy and paste it over. You can redraw it over here if you'd like. Definitely would suggest doing that. On this side, it still has 6 protons and it still has 6 electrons, but we are going to change the number of neutrons. So there's no longer going to be carbon 12. This is now carbon 14. So it's still the number of protons plus the number of neutrons, but where or how many do we have of each? Well, we cannot change the number of protons, remember? So that still has to be 6. So what do we need to add 6 to get to 14? Oh, that's right, we need, asterisk, we need 8. There are 8 neutrons. So essentially we've added 2 more neutrons in here, okay? So some people think, well, if neutrons are here to stabilize the atom and having a stable atom is good, then adding neutrons would be a good thing. You'd think that, but they tend to get in the way. Nature has a way of balancing things out. 6 protons and the 6 neutrons, 6 electrons is perfect. It doesn't need any more balancing. You start adding more and it starts to destabilize. Either too much destabilizing. If you took away, it'd be too less neutrons destabilizing the atom. So what happens when we start to add those neutrons to here? Well, they get in the way and it causes the atom to vibrate more, and it starts to release energy. And when it does that, what's happening is it's breaking bonds. All right, so it starts to release energy. Oops. Let's get that. There we go. Starts to release energy. And what does it do? Well, what do we call it when atoms are slowly releasing energy over time? We call this radioactive. Not that you can see that because it's all written in this dark color. There we go. These are radioactive. Okay? So what's happening in here is they are unstable. And unstable. I knew I had that wrong. Y'all, I'm a terrible speller. I apologize. They're simply unstable. So they start to release some of the energy. What's happening is those bonds between the electrons and protons are being disturbed because there's just too many neutrons in the way, and they're starting to break down. And so they slowly start to release this. So things that are radioactive and unstable, they're giving off energy. Right? And we can use that energy to drive different systems. If you think about like the big submarines that are driven on nuclear power, what nuclear power are they using? They're using that strong nuclear force. They're using uranium, which is radioactive. It's an isotope. It's a uranium atom that has a different number of neutrons in it. It's making the atom unstable, so it's giving off energy. We can harness that energy and use it for power, though it's not the best for us because radiation is deadly to humans. So you're probably thinking, carbon-14, wow, that's so weird. How would I do that? It does this all the time in nature, all the time, and it's actually not that harmful to us, though we have these little devices called Geiger Meters, and we can use it to trace radiation. And one of the things I'll use carbon-14, if you've ever been to, or seen somebody get a CAT scan before, what they do is they inject somebody with a molecule, and that molecule has attached to it a carbon that is a carbon-14 instead of a carbon-12. So it's a slightly radioactive carbon attached to some type of biomolecule that they inject into your body. That biomolecule is something that usually attaches itself to a specific type of protein that's found on cancerous cells. So what they do is they inject you with a radioactive liquid with those biomolecules in it, and we call those tracers. Why? Well, give you after you do the injection, about an hour later or so, or whatever time frame, they go through and then they plug you in this CAT scan, and they scan your body, and they're looking for where the radiation is. Where are these carbons ending up in your body? Well, if they're all around a certain spot, well, that's where the cancer is, because the biomolecule that this carbon is attached to is specifically looking for the proteins found on a certain type of cancer. So this is how they can tell where cancer is. They use this in other experiments all the time. They did a famous experiment with trees once. They put a bag around a branch of a tree, filled it with carbon, because plants love carbon dioxide, right? And the carbon dioxide had carbon-14 in it, and they left the bag on the branch and let it absorb the carbon. And then they came back the next day, or actually a few days later, probably even like a week later, maybe even a month. And they say, well, okay, well, let's see where the carbon has gone. Is it gone down to the roots? Like most people think, well, hey, yeah, the carbon comes in, through photosynthesis, it's turned into sugar. The sugar is probably stored in the roots. One thing they found is that it was in the roots, but it was also in the roots of other trees. And some of the trees on further down, and further away from the original tree, they had all formed a network where the trees were helping each other out and sharing some of their water and sharing some of their nutrients and sugars with each other by simply interconnecting their roots. And it was a big discovery that, hey, these trees are all helping each other out, that the community and the population in the community of trees and plants all around it was important enough to where nature has selected for this type of evolution, to where sharing nutrients through the tree roots would be a good thing. So, okay, so that's cool. That's enough about isotopes. So now let's jump over and let's talk a little bit about the different types of chemical bonds.